Okay, this is AP Calculus BC, and in this video I'm going to go through section 3.6, which is primarily focused on L'Hopital's rule. In this section we're also going to discuss the idea of indeterminate forms, since that is something that we need to know to be able to properly apply L'Hopital's rule. So before we get into L'Hopital's rule, let's just talk about the idea of an indeterminate form. The reason this is important is because L'Hopital's rule can be applied anytime we see the indeterminate form 0 over 0 or infinity over infinity. So we've got to be able to identify when we're seeing forms where L'Hopital's rule could potentially be helpful. Okay, so to start with here, we have some determinate forms. And it doesn't necessarily mean that you know what the sum or the difference or the value is. It just means that you know what the result is going to be. So for example, if I were to add two infinitely large numbers, I know the result of that is going to approach infinity. Or same thing, if I have two numbers that are approaching negative infinity and I combine them, I know I'm approaching negative infinity. 0 raised to any power is always going to be 0. And 0 raised to the negative infinity power, this is a little bit trickier, but if you think about it from the standpoint of having like a 1 over something very close to 0, then you can see how that would approach approach infinity. Okay, so those are what we call determinate forms. Now, the ones that we really want to focus on here are these indeterminate forms. So L'Hopital's rule is going to be a way for us to solve limits using derivatives. And these are the two forms that we're typically looking for, 0 over 0 and infinity over infinity. Now, there's some other indeterminate forms that may not fit 0 over 0 and infinity over infinity when you first look at them, but with some manipulation, oftentimes we can take these other forms and turn them into a 0 over 0 or infinity over infinity. And we'll see that as we go through a lot of these examples. So the first indeterminate form, infinity minus infinity, I don't know how fast either number is approaching infinity, so there's no way for me to do a number operation with that. Also, 0 times infinity. Infinity is not an actual numerical value, so I can't just multiply by 0. So that's considered to be an indeterminate form because we're trying to do a mathematical operation with a concept. 0 to the 0 power is a little bit of a tricky one, but if you think about anything raised to the 0 power is 1. However, 0 raised to any power is going to be 0. So when I start looking at right and left side limits, it starts to make sense why this would be indeterminate. This one we don't see as often, the 0 to the 0 power, but it is considered to be an indeterminate form. 1 to the infinity we're going to talk about a little bit later on. And then infinity to the 0 power, it's the same idea again of trying to perform a mathematical operation on something that's not actually a number. So raising something to the 0 power you might think is always going to be 1, but remember infinity is not a number, so we can't actually work through and solve that out. Okay, so here is L'Hopital's rule, and there's actually two forms for L'Hopital's rule. You can see this one that I have on the screen is for infinity over infinity. However, the same rule actually applies when we see 0 over 0. Both of the forms of L'Hopital's rule can be proven using the definition of derivative. It's kind of definition derivative combined with solving a limit. And they have that worked out in your textbook if you're interested in how it actually works. But what I'm going to do here is I'm going to go through the rule and make sure you understand the rule and where it's appropriate to use it. So in this explanation, what we're talking about is a rational function. And anytime we talk about L'Hopital's rule, we'll be talking about taking the limit of a rational function. So what they're defining here to be the numerator is f of x and the denominator is g of x. And you can see that in this setup that they have down here where we're trying to find the limit of this rational function, f of x is the numerator, g of x is the denominator. Both of those limits are getting infinitely large. So if I take the limit of the numerator and the limit of the denominator, they're both approaching infinity. What L'Hopital's rule says I can do is if that's the case, that limit that we started with is equivalent to the limit of the derivative of the numerator divided by the derivative of the denominator. Notice that that's not the quotient rule. It's not the derivative of the original function, the original rational function. It's the derivative of the numerator divided by the derivative of the denominator. So we'll go through a bunch of examples in how this works. So here's an example. Find the limit as x approaches 1 of x squared plus 2x minus 3 over the natural log of x. And like it says here, notice that if you plug 1 in, you're going to get 0 over 0. So that's basically justifying that I can use L'Hopital's rule here because I see that 0 over 0 is showing up. Typically, just to show my work appropriately, I try to justify what's happening so there's not some sort of magical step going on in my work. And what I'm doing here is above the equal sign, I wrote LH just as a shorthand for L'Hopital's rule. So that's justifying that, okay, I'm applying L'Hopital's rule here. And the reason I can do that is because I've stated that I've seen 0 over 0 showing up in this. So now when I apply L'Hopital's rule, I'm going to take the derivative of the numerator, which would be 2x plus 2, divided by the derivative of the denominator, which would be 1 over x. And then from there, I've got it in a form where now if I plug 1 into the numerator and the denominator, I'm actually going to get a numerical value for a solution. And you can see this is actually going to be equal to 4. Okay, so that's essentially what L'Hopital's rule is. And that's a really basic example of it, but that's the idea of it. We're looking for 0 over 0 or infinity over infinity. And when we see that with our limits, we can use L'Hopital's rule as an alternate method to solve these out. Like I mentioned before, there is a proof for it in the book. I'm not really going to go through it here, but the proof is fairly simple. And you can read through that and see how it involves the definition of derivative. Okay, so here's a limit that we saw a while back, a couple of weeks ago when we were in our limits unit. And at the time, we proved this with the squeeze theorem and just basically memorized this limit. Well, the limit as x approaches 0 of sine x over x is equal to 1. We know that to be the case. But think about if you did substitution here, you would actually get 0 over 0. So that's giving me the form 0 over 0, which is an indeterminate form. That means that I can actually rewrite this as an equivalent limit using L'Hopital's rule. So again, I wrote the LH above my equal to, indicating that I'm applying L'Hopital's rule. And now I've got cosine x divided by 1. And now when I do my substitution, you can see that we get 1, which is the result we knew we were going to get. But now we have another method to solve that type of a problem. The two things that I want to note here, this is justifying my use of L'Hopital's rule. I'm showing that I do have one of those two indeterminate forms. And this is explaining what happened from the first original limit to now the equivalent limit. Okay, so here's another example. We've got tangent x minus x over x cubed. We're taking the limit as x approaches 0. When you first do substitution here, you can see that you're going to get 0 over 0. So that means that L'Hopital's rule is appropriate to apply. And I'm going to write an equivalent limit. And the derivative of tangent would be secant squared. So I have secant squared x. Derivative of x is 1. So secant squared x minus 1 over 3x squared. Well, let's try to do direct substitution now into this. And what you see is you actually get a 0 in the numerator and a 0 in the denominator again. So L'Hopital's rule didn't lead directly to a solution in this case. However, since we have seen that the 0 over 0 showed up again, I can actually continue to do L'Hopital's rule. I can have another step of L'Hopital's rule because I'm still seeing an indeterminate form that's 0 over 0. So I'm going to take the derivative of the numerator and the denominator again. And in this case, I get 2 secant x times secant x tangent x, or 2 secant squared x times tangent x, all over 6x. Well, do your substitution again. Unfortunately, we end up with 0 over 0 again. Now, when you start to run into this type of a situation, you don't want to just blindly continue on forever. What we do want to identify is, does it look like we're making any progress here? Because we're continuing to see 0 over 0. Well, look at the denominator, and you can see that the degree of the denominator keeps decreasing. So actually, I know on the next step, I'm going to come to some sort of a conclusion about what this limit is going to be, because when I take the derivative of 6x, I'm going to get 6. So I'm going to do L'Hopital's rule one more time. And when I go through my process here, in the numerator, my derivative is starting to get kind of messy, but I have 2 secant to the 4th x plus, let's see, 2 tangent x times 2 secant squared x tangent x. Okay, so essentially what I've done there is the product rule in the numerator. And now in my denominator, I'm going to get 6. And at this point, if I evaluate this limit, remember I'm plugging in 0 for x. So this part of it is going to become 0. And essentially I've got 2 over 6, which is going to be 1/3. And you could check that graphically on your calculator if you want. And you'd see that that limit is actually going to be equal to 1/3. Okay, so notice the repeated L'Hopital's rule there. So we can do that when necessary with L'Hopital's rule. All right, so here's an example of why you want to be careful. So the thing with L'Hopital's rule is that it's a really powerful tool. However, if used incorrectly, it's going to give you essentially garbage as a result. And I wanted to show you this example. So for this one, we have the limit as x approaches pi from the left of sine x over 1 minus cosine x. And when I plug pi into this, in the numerator, I'm going to get 0. In the denominator, I'm going to get 2. So without even really doing a lot of work there, I can see that the limit is actually going to be 0. Now, let's say you didn't check to see if you had an indeterminate form and you just tried to blindly apply L'Hopital's rule. Let's say you went through and you said, all right, I'm going to use L'Hopital's rule here. And that would give me the limit as x approaches pi from the left of cosine x over sine x. Well, sine of pi is going to be 0, so this is approaching a vertical asymptote. This is actually going to approach negative infinity if I try to solve it that way. And the reality is this limit does not approach negative infinity. And this is why you've got to be really, really careful, because this is completely invalid because I didn't have an indeterminate form where that would allow me to apply L'Hopital's rule. So be careful with it. It's a really nice tool, but only when used appropriately. Okay, so let's go through some examples of a little bit more advanced type of situations now. So sometimes you're going to see indeterminate forms like different ones that we talked about earlier. So not necessarily 0 over 0 or infinity over infinity. So on this next one, it says take the limit as x approaches infinity of x squared e to the negative x. If I just do direct substitution, you can see we essentially have infinity times 0, which was one of our indeterminate forms. Well, here's the graph. I can tell that this limit is going to approach 0 as x approaches infinity, but let's actually go through and solve this out using L'Hopital's rule. So this is equivalent to the limit as x approaches infinity of x squared over e to the x. So what I'm trying to do here is take an indeterminate form that I couldn't work with in terms of L'Hopital's rule and rewrite my function in a form where I can use L'Hopital's rule. And you can see in this alternate form of the function, now I have infinity over infinity. So now the use of L'Hopital's rule is justified. So I can now use L'Hopital's rule, and this becomes the limit as x approaches infinity of 2x over e to the x. Well, unfortunately, we still have infinity over infinity. But you can see that if we were to continue on, the next step, I'm going to come to a solution here. So I'm going to use L'Hopital's rule again. So I've got the limit as x approaches infinity. And here I've got 2 over e to the x. And now when I apply that limit as x approaches infinity, this is going to approach a value of 0, which is what I was expecting based on the graph. Now the reality is I didn't even need to use L'Hopital's rule here, because when I got to this form, if you know your orders of magnitude, you know e to the x grows much faster than x squared. I could already tell it was going to be 0, but you can see that you can still use L'Hopital's rule. It's a valid application here. Okay, so here are some more similar types of questions where we've got limits that are in forms that don't necessarily fit the form that we need for L'Hopital's rule. So these are all in the form of 0 times infinity. So the first two are 0 times infinity, second two are infinity times 0, but essentially we have them in a form where we have an indeterminate form. But notice on any of these, and I'll just choose this one over here, if I were to rewrite this as the limit as x approaches infinity of x over e to the x, I rewrote it as a rational function. Now you can see how we have infinity over infinity. So a lot of times what we're going to do with these to solve them is we're going to do a little bit of algebraic manipulation. Okay, so let's take a look at a few more examples. So we'll get into some that are, like I said before, a little more complex. Sometimes the use of L'Hopital's rule is not as apparent. So here we have the limit as x approaches 0 from the right of x natural log of x. So what we have here is essentially 0 times infinity. Well, rewriting this as a rational function might not be really obvious this time, but once you've seen it once, you'll kind of think of doing this the next time. But we can really rewrite any function as a rational function, because I can make this natural log of x over 1 over x. And now essentially what I have is negative infinity over infinity. So I essentially have infinity over infinity. So since I have that indeterminate form, so we know this would approach negative infinity, this would approach infinity. Since I have that indeterminate form, I'm now justified to use L'Hopital's rule. And I can say the limit as x approaches 0 from the right. In the numerator, the derivative would be 1 over x. In the denominator, it would be negative 1 over x squared. It's not obvious right away, but it's pretty easy to see with just a little bit of algebra here. I can rewrite this as the limit as x approaches 0 from the right of negative x squared over x. And now the x's will cancel out, and this is going to turn out to be 0. Okay, so again, just a different situation where we've got an indeterminate form that wasn't a 0 over 0 or infinity over infinity, and we rewrote the function so that it fit the form that we wanted. All right, so here's another example that I want you to try. So we have the limit as x approaches pi over 2 from the left, and we have secant x minus tangent x. So this is an infinity minus infinity form. So try to think about how you can rewrite that function so that it's in a form where you can apply L'Hopital's rule. So just pause the video, take a minute, work through that problem, and then unpause it, and I'll show you the solution. Okay, and here's what you should have ended up with on that one. You can see that secant is the same as 1 over cosine, tangent's the same as sine over cosine, and then from there, I've basically rewritten this with the common denominator of 1 minus sine x over cosine x, which is essentially 0 over 0, if I try to do direct substitution. So using L'Hopital's rule, I can then take my derivatives, and in the end here, when I rewrite this, you can see I get this form from my derivatives of negative cosine x over negative sine x, which is then going to give me 0. Okay, so it's not that difficult in most cases to manipulate these alternate indeterminate forms into the two that you want, but sometimes you've just got to be a little bit creative with your application of algebra to make that happen. Okay, so let's take a look at just a couple more. The most difficult type of problem typically for most people are the ones that involve 1 to the infinity power. And I just wanted to make it really clear why 1 to the infinity is considered an indeterminate form. Because you might think, well, 1 raised to any power is still going to be 1. But what we have to do is consider the behavior of that from a one-sided limit perspective. So if I have a number just slightly larger than 1, so like 1.01 or 1.001 or 1.0001, if I take the limit of that as x goes to infinity, I'm multiplying by more than 1 every time. So eventually, that's going to get infinitely large. Same thing as I approach 1 from the left, like 0.99 or 0.999, anything really, really close to 1. Well, when I raise that to a power, I'm multiplying by less than 1 every time. So eventually, that's going to approach 0. So you can see how what's happening on the right side of 1 and what's happening on the left side of 1, it's not matching up. So in the end, 1 to the infinity power then is considered to be an indeterminate form. Okay, so like I said, these are the kind of the trickiest ones. And what makes them tricky is that we have to do some of the stuff that we did back when we were talking about logarithmic differentiation. So look at this first problem. You can see that we've got limit as x approaches 1 of x to the 1 over 1 minus x. And essentially, that's going to be 1 to the infinity power. Okay, so 1 to the infinity power is not one where we can apply L'Hopital's rule. So what I'm going to do is I'm going to define my function. I'm going to say y is equal to x to the 1 over 1 minus x power. And now I'm going to manipulate this so that I can get this in a form where L'Hopital's rule will work. I'm going to take a log on each side. And the reason I'm going to take a log on each side is because I need to make a rational function show up so that I can apply L'Hopital's rule. And you can see this is actually the same as the natural log of x over 1 minus x. Now, with that being the case, now I can go through, and remember, we were taking the limit of the function. Well, now that we've taken the log of the function, I can still take the limit of the function. I just have to remember at the end that this is the limit of the log of the function. So the limit as x approaches 1 of natural log of y would be equal to the limit as x approaches 1 of natural log of x over 1 minus x. And if I plug 1 into that, I'm going to get 0 over 0. So I've made the form that I wanted to, or one of the forms that I wanted to show up, I've made it show up. So now at this point, I can use L'Hopital's rule, and I've got the limit as x approaches 1, and it would be 1 over x over negative 1. Plug 1 into that, and you can see we're going to get negative 1. Now, remember, that's not going to be the solution for the original problem. This is the limit of the natural log of the function. So what I need to do is I need to convert back. If I want the limit as x approaches 1 of x to the 1 over 1 minus x, I've got to remember the opposite of taking a natural log is taking an exponential and raising it to that power. So this would be e to the negative 1 or 1 over e. And that's the step that often is forgotten. A lot of people can kind of make sense of this step where we took the log of each side, but when they get to this part, a lot of times people think, oh, well, that's my solution. But don't forget, we have to undo what we did at the beginning of the problem. So when we manipulated it to make it work, this time, yes, we manipulated both sides of the equation, and we sort of changed the form, but we also changed the function this time because we took the log of the function. We didn't just rewrite terms that were already there. So we have to undo taking that natural log, which is taking the base e and raising it to the power of the result. Okay, so I've got another one of these here that I want you to try. And on this one, we have the limit as n approaches 0 of 1 plus n to the 1 over n power. Some of you may be able to recognize that and know what the solution is, but what I want you to do is just try to work through that. Okay, so pause the video, work through the problem, and then when you unpause it, I'll show you the solution. Okay, and here's what you should have ended up with, and I apologize for my kind of messy handwriting on this one. But in the end, this is actually one of the forms of E, and we've seen that before, so you may have recognized that. But in terms of solving it out, it's just like the one we just looked at. So you can see that we have y is equal to 1 plus n to the 1 over n power. So I took the natural log on each side. That allowed me to rewrite this function in the terms of natural log of 1 plus n over n. And now I'm going to apply the limit to the natural log of my function. And you can see I get 0 over 0. In the end, that limit, when I do L'Hopital's rule, is going to give me 1. So the last step then is to convert back. You can see down at the bottom I got 1, but my actual solution is up here because I converted back. So opposite of taking a natural log is using that base e. So I have e to the power of 1, or just e. Okay, so not really that difficult to do. All right, so the last part here, I've got 4 more problems for you that I just want you to try. Some of these you may be able to do without L'Hopital's rule, and if you can, do it. If you can't, though, now you've got L'Hopital's rule as a fallback option to solve these out. So I want you to pause the video and try to solve these 4 limits any way that you can, and then when you unpause the video, I'll show you the solutions. All right, so here's what you should have gotten for those last 4, and I didn't even show work on these. Especially the first 3 are 3 that you can figure out without even really using L'Hopital's rule. The first one, you can see the degree of the denominator is bigger than the degree of the numerator, so we know we're going to get 0. The second one, we saw, remember, sine x over x, the limit as x approaches 0 is 1. Well, this is a modified form of that. So we've seen questions like this. Essentially, it's like thinking of sine 3x over x divided by sine 5x over x. And that would give me 3/5. This one down here at the bottom maybe is not quite as obvious, but it boils down to orders of magnitude again. So think about your numerator. This is a natural log function, which is going to kind of flatten out and have a slope that gets closer and closer to 0 as x gets larger. x cubed is just going to get steeper and steeper and steeper the higher the x value gets. So x cubed is growing faster than the natural log function. So with that being the case, the denominator is growing faster than the numerator. I know it's going to be 0. Now, the nice thing is let's say you didn't recognize that. Now you've got a fallback option. At the beginning here, you could call that infinity over infinity, and then you could go through and you can use L'Hopital's rule and you can solve that out. All right, and then the last one is another one where we have the form. In this one, we would have essentially 1 to the infinity power. And this would be another one where you would involve taking the log of the original function so that you can move the 2 over x down, create a rational function, and then apply L'Hopital's rule to that. You'll end up with a limit value of 4, and then just convert it back to e to the 4th. Okay, so these are not super difficult questions once you've seen how they work. The big thing is, don't feel like you have to use L'Hopital's rule every single time you see a question. Number one, it could give you a wrong answer if you're using it in a place where it's not appropriate. And number two, you might be wasting time. If you look at a question like this one, for example, there's no reason for me to use L'Hopital's rule there. So this is just kind of another tool for us to use when we're trying to analyze these limits. And you might wonder why this is important, because we already did limits unit. The reason that this is important and why we spend some time on it as it pertains to this class in particular is that when we get into our series unit in the second semester, we're going to need to take limits of functions that look like this a lot. So we have to know how to be able to use L'Hopital's rule in these more advanced situations. All right, last thing that I want to mention, there is a worksheet attached to this set of notes. This worksheet is not something that you have to do. This is just extra practice. The top part of this is just going through and actually solving the limits in 2 different ways. But down at the bottom, what you're supposed to try to do is use L'Hopital's rule if it's appropriate. And you can see I have number 11 circled. There's kind of special behavior on number 11. So try to check that one out. Even if you don't do the worksheet, try to check out number 11 and see what happens on that one. You don't have to turn in the worksheet. It's just for extra practice. You should get enough practice in the Wiley Plus homework that you should feel pretty good about it. But if you feel like you need extra, there's a lot more problems here. And you can see on the last page, all of the solutions are there as well.